If you want to learn statistics for data science, where do you even start? We are all suffering from information overload. If you pick up any statistics books, you might come across a lot of traditional statistical concepts that might not be any longer relevant or important in the modern data science. That's why I have put together a short list of the basic statistical concepts that are most useful from data science perspective, and I will also explain why in this video we are going to cover statistics for exploratory data analysis, where we discuss the estimates of central values and variability, data distribution, correlation, and exploring variables. Next, we look at data and sampling distributions, where we talk about sampling, bias, sampling distributions of a statistic, the bootstrap, confidence intervals, and an overview of the main types of distribution. Again, to avoid information overload, we are not covering the more specialized topics such as discord experiments and significance testing, regression, statistical machine learning, and unsupervised learning. This is because I believe these topics might not be relevant for you unless you are doing machine learning or hypothesis testing in your work. So I will leave these topics for the future videos. Now let's get started. The most basic topic in statistics is probably the estimates of central value and variability of the data. They are going to be your bread and butter when you are doing descriptive analysis on your data set. I'm pretty sure most of you are already familiar with both of these concepts. The most basic estimate for central value is the mean, also known as the average value. A variation of the mean is a trimmed mean or truncated mean, which is the average of all the values after dropping a fixed number of extreme values. Another variance of the mean is the weighted mean or the weighted average, which is sum of all the values times the weight divided by sum of the weights. For categorical variables, we can't calculate the average, so instead of that we use mode. The mode is the value or values in case of a tie that appears most often in the data. And we also often look at median, which is the value such that one half of the data lies above and other half lies below it. And lastly, we have outlier, and as suggested by its name, it is the data value that is very different from most of the data. Now let's look at different estimates for variability of the data. Firstly, deviation is the difference between the observed value and the mean. It is also known as errors or residuals variance, aka mean squared error. It is the sum of the squared deviation from the mean divided by n minus 1, where n is the number of data values. Now, you may ask why it is divided by n minus 1 instead of n. There is a long story behind this, but basically it is the correction of the underestimation of the true variance of the population using a sample. Standard deviation, also known as Euclidean norm, it is simply the square root of the variance mean. Absolute deviation, also known as Manhattan norm, it is the mean of the absolute value of the deviations from the mean. Another useful statistics is a range. It is a difference between the largest and the smallest value of the data. You might also have heard of percentile, which is a value such that p percentage of the value take on this value or less, the interquartile range. It is basically the difference between 75th percentile and 25th percentile. When comparing two or more variables together, there are different techniques you could use depending on whether two variables are numerical or categorical. Scatter plot, heat map, hexagonal binning, and contour plots are useful when comparing two numeric variables together. They all give us a visual representation of the two-dimensional density. When it comes to comparing two categorical variables together, a useful way to summarize them is to use contingency table. A famous example of contingency table is a pivot table in Excel. When you want to compare a categorical variable with a numeric variable, box plots are usually a simple way to visually compare the distribution of a numerical variable grouped according to a categorical variable as shown in this example. While box plots are useful and more clearly show the outliers in the data. Now let's move on to the next topic, which is the data and sampling distribution, which is the core of statistics. One of the key concepts to understand is that when you collect data, use sampling from a population. There are different types of sampling. The two most widely used are random sampling and stratified sampling. Random sampling is simply drawing elements into a sample at a random. Random sampling makes sure that your sample are representative of the larger population it was meant to represent. In stratified sampling, the population is divided into strata and random samples are taken from its stratum. The term sampling distribution of a statistics might sound a bit confusing at first, but basically it refers to the distribution of subsample statistics. For example, the mean over many samples drawn from the same population. The distribution of a sample statistics such as mean is likely to be regular and bell-shaped than the distribution of the data itself. Central limit theorem receives a lot of attention in traditional statistics books because of its underlying machinery about hypothesis testing and confidence intervals, which themselves consume half of the space of those books. We as data analysts or data scientists should be aware of this theorem, but since formal hypothesis testing and confidence interval play a very small role in modern data sciences, the central limit theorem is not so essential anymore in the practice of data science. An important measure of the sampling distribution of a statistic is the standard error. It is the metric that represents the variability of the sampling distribution for a statistics, and please do not confuse standard deviation, which measures the variability of individual data points, with standard error, which measures the variability of a sample metric. Central limit theorem is often calculated by the formulas, especially the t-distribution. The most important distribution is probably normal distribution. Despite being called normal, the normal distribution data is generally not normally distributed. Sometimes the distribution is highly skewed or asymmetric, such as with income data, where most people would be on a lower income side and only a few very small percentage of the population would have a very high income, like millions. Assuming a normal distribution is very dangerous, as it can lead to underestimation of extreme events. There are also other distributions that serve different kind of purposes, such as t-distribution, as we mentioned earlier, binomial distribution, Poisson distribution. But in the scope of this video, I will leave it up to you to get to know about them, because these distributions only have very specific use cases in data science and most of us won't use them very often. Okay, now you have had a glimpse of the basic statistics that you need to know, but how much is more? How much is enough? In my opinion, the depth of the knowledge that is expected varies quite a lot across different roles in the data science. For example, if your role is deep in the engineering side or business side of data science, then you might not use as much statistics as you would if you are a data analyst or data scientist. You might just do fine not knowing much about the fancy machine learning models or Bayesian statistics if you are not going to do any machine learning at all. I hope with this video you have had a better idea of the most important statistics for data science, and this is the foundation, and it's up to you how much you want to expand or advance it in the future. Please like and subscribe to my channel for more such videos. Thank you for watching and see you next time.